Hello ladies and gentlemen, I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to talk to you about my latest article. It's entitled The Planet X System and the Reacting Sun. Now the Sun on October 4th, 2017 seemed to be undergoing two effects due to the presence of the Planet X system. Now, in the months of our observing the stellar cores in the Sun's corona, I have been led to make some conclusions, and I have written a lot of articles about it. I can only summarize them here. The Planet X system seems to have come from the south of the ecliptic, and it was found by Dr. Harrington. The Nemesis system was found north of the ecliptic in the constellation Orion and came in from there. The stellar cores currently clustered around the Sun, and previously I have called them brown dwarf stars. Now I call them stellar cores because that's what they look like, exposed cores of stars that have aged. So they probably came in with either one or even more likely both systems. These old stars connect magnetically to each other and other stars and do not move as would be expected if they obeyed the gravitational interaction. They draw plasma and energy from main sequence stars like the Sun and have been around it since at least, that is our Sun, since at least the 1990s. I have written some articles where I have shown pictures from 1996 showing that these objects were there already. Now their number seems to have increased, and they may still be increasing. They are not likely to ever leave the Sun and may have connected to the Planet X main star or Nemesis in the same way, probably to both. Nemesis has been a dead star for a long time, and the Planet X star is also old and weak. It only emits dim red light. So the Sun is the only star of these three that has enough fuel and will therefore attract most of the stellar cores. Now the Sun seems to strongly attract these dead stars, and they seem to rejuvenate and resume light emission after some time in the Sun's corona, and may then settle in a stable but very close orbit around the Sun. So basically they have joined the nucleus of the Sun, and that's what they seem to remain. They are not likely to leave the Sun unless a stronger main sequence star than the Sun passes by and attracts them. However, since they are locked onto the Sun, it is likely that the Sun would move with them towards this other star in that case. So in figure 1, I'd like to start showing what these stellar cores have done to our Sun. And this is an image from 2011 in the 304 angstrom wavelength. It's an SDO image, the Solar Dynamics Observatory. It was launched in 2010. So here are two images. This is from 2011, this is from 2017. And before anyone mentions that it may be to do with the fact that we're getting close to the solar minimum, I'd like to add that the solar maximum was in 2014. So 2011 was 3 years away from the solar maximum, and 2017 is also 3 years away from the solar maximum. So it cannot be anything to do with that. We basically have the Sun in this wavelength not being able to emit light of the same intensity. In other words, the number of photons leaving the Sun has decreased substantially. And here are images. This is the 2012 image. This is the 2013. You can already see there's a difference in the intensity of the light. Notice this cannot be due to a resetting of the tones for each intensity, because the brightest regions are exactly of the same tone, this whitish yellow. And you can see the 2013 image, again, substantial decrease in intensity of the light emitted by the sun. We still had sunspot regions. We still have bright emission from certain areas. These bright regions are about the same. The sunspot regions, well, there's still one small, very bright one there. And then we see a substantial decrease between the 2014 and the 2015 image. Even more in the 2016. And now the 2017. And to tell you the truth, it's saddening to see our sun weakening to such an extent in just a few years. And this has to be due to something affecting it. This is not just due to an approaching solar minimum. This is the sun at the solar maximum. But even at solar maximum, it's not as the light intensity was not as much as in 2012. So, and that is the broad daylight from these regions of the sun. Now, the 304 angstrom light gives us images from a certain region of the sun, and that region is the transition zone between the chromosphere and the corona. So this is the light emission from just below the corona. And we can see it has decreased substantially. So the wavelength of the light is the same in all images. Remember, this is 304 angstroms or 30.4 nanometers. The wavelength is associated to the energy of each photon. So the photon, each photon that impacts the detector has the same energy. It's associated to this wavelength. But what has decreased is the intensity of the lights. So the brighter regions show a greater intensity, and the intensity is associated with the number of photons emitted from that region. So this means that as the years have gone by, the sun has been able to emit less and less photons from the same region. And what I have noticed, but I couldn't quite show it in this article because it's more obvious in the video that you can download, the 48-hour video. And this showed that there were these tiny sparks happening all over the sun. Now, these tiny sparks were about the same color as what the sun may have been all over. These tiny, slightly brighter sparks than the rest of the sun. It could have been seen at the edges here. And they were happening all over the sun. And to me, that looked like the sun is actually having trouble staying ignited. Because where it was continuously ignited all the time at the top of the chromosphere, it's now just sparking on and off, on and off, on and off. So it looks like the sun is having trouble staying ignited. Now we have evidence of these telecores in the sun's corona. There are just some of these images where, to me, it's the clearest. This is a cactus image, which is, of course, based on the SOHO spacecraft images, the chronograph. And you see one of these images here, and you can clearly see a spherical object inside the CME. The cactus coronagraphed images are designed to show CMEs very clearly. The sun, of course, is a lot smaller than the occulter. It would be about this size. So this object is just slightly smaller than the sun. And this object is slightly larger than the sun. You can clearly see the spherical edge of this object where light seems to be reflecting off it on both sides. Only a solid object can produce this sort of outline. So we have stellar cores in the sun, and these objects are absorbing energy from the sun and therefore weakening it, and they are also provoking the sun into having stronger solar flares and CMEs. So, and the way they do that is through their magnetic connection. They draw the sun's magnetic field outwards. The sun uses the magnetic field to hold on to its plasma. So when its magnetic field is pulled outwards, and therefore it has trouble holding on to its plasma, and so the associated explosions that we see that are due to the outward directed electric field become much larger than the sun would have been if it wasn't being provoked. Now, another image that I really enjoy using is the one of the blue stellar core. This was an amazing thing that happened where I could see, and Scott was the one that first photographed this object, what these objects really are. They are solid objects in the sun's corona. The grooves tell us that they are solid, and they remain solid in the sun's corona, so they have to be extremely dense not to melt and vaporize. And we do know that stellar cores of stars have a density of 150 grams per centimeter cubed, which is much greater than that of a star. The sun's corona is so hot that it would melt the core of, say, Earth, which only has a density of about 13 grams per centimeter cubed. So they have at least 10 times greater of a density than the core of a planet. And our planet would melt, our planet's inner core would melt at about 7,000 Kelvin. So the fact that these objects do not melt when they are in the sun's corona tells us they are extremely dense. They are stellar cores. They are the exposed centers of stars which formed during the star's main sequence phase. And we can see here this object is connecting with the sun magnetically. There is plasma being drawn from the sun's corona. You can see the connection here. This is exactly the same thing that stars in the white dwarf phase do. And we can see that there is pink plasma gathered along the bottom of this object. And this tells us that this plasma is ionized and it's giving off pink light. And pink light is red and blue mixed, so the green part of white light is missing from there. I do still find that very strange that these objects emit this pink light. But now this means that this light that's being emitted from this gaseous plasma, which is obviously somehow either coming from the sun or coming from a star that was a stellar core, that is a stellar core that has rejuvenated and is emitting now this light because its own corona is producing light of this color. I'm not actually sure of what is happening. Either this object is ionizing the plasma that it's gathering so that it's emitting this light, or there is a rejuvenated stellar core just behind the sun that is ionizing its plasma that it gathered from the sun anyway to emit this color. So this photograph was taken by an astronomer in Germany, and it's the second set of photographs that we got. The first ones Scott took through his own telescope, of course, and these are revolutionary. I think they are amazing, and they show us so much about what these stellar cores really are. Now, we do know that we have rejuvenated stellar cores because we have stars that are close to the sun that are emitting this light and illuminating our atmosphere with this pink light. Our sun cannot be the source of this light. Our sun, of course, emits white light. And even if the sun has changed, and I have just shown you that it has, we are still getting blue skies, and green plants still look green. So obviously the green light, there's still green light coming from the sun. So the best explanation for this is that we have additional objects that are emitting this light. And here it actually looks like there's one in the sky, there's the spherical shape in this image. Now, some of the stellar cores in the sun's corona can drain the sun to such an extent that it actually stops emitting light. This is what I have observed during the SDO eclipse, and possibly that is the reason why I was initially attacked and why eventually I left South Africa, was because of my assertion that the sun goes dark during the SDO eclipse. And I have shown irrefutable evidence to that, and it comes from the fact that the sun's corona shrinks as the darkness advances, so that cannot be explained by an eclipse at all. No one can explain it. And if someone can explain it to me, then I suggest that they do send in the explanation. But as far as I'm concerned, there is absolutely no way that a solar eclipse can cause the sun's corona in the still lighted part to shrink back towards the surface of the sun. And I have shown that in many of my articles. But now here what we see is the sun doesn't seem to go completely dark. It seems to lose partially lose light emission, and we can see that by looking at the edge here. Now, several cutoff lines are used. We see here on the top horizontal and this vertical line. So these hide parts of the sun. And of course, it takes effort to add cutoff lines to each image. And I don't think that anyone in their right mind would do this if there wasn't anything to hide. So that means that the cutoff lines are there to hide objects in the sun's corona. And these 193 angstrom images specifically show higher up above the chromosphere, and they show the sun's corona. So this means that there are objects there, and these objects absorb plasma from the sun, so they would be enveloped in the sun's plasma, so they would be visible. Sometimes it's not quite easy to see. They are actively being hidden in several ways, but the fact that cutoff lines are being used means that this is the only way that they could hide what was there, and that is by not showing that portion of the sun. Now, there is a cutoff line also used here. This one is made out of several straight lines that form a sort of a curved line. The same is used here, but what is left shows us what actually is happening to the sun. As you can see, this boundary is jagged. There are dark portions at that boundary here. And the portion just above the boundary in the lighted part of the sun, it's much darker than we'd expect. If we compare the same region, and this image is from just 15 minutes before this image, you can see there's no darkness here in this region that could possibly explain the darkness we see here at this edge. Nor is there any dark little spots that could account for the dark little spots we see along this boundary. And this shows that the sun has lost light emission in this region. And the fact that the rest is hidden, to me, means that it was probably all dark in this region over here. This is not due to even an ellipse. This can only be to the sun losing light emission in this wavelength, 193 angstroms. And the same thing happens with other wavelengths. This is the X-ray wavelength, the 94 angstrom. Again, we can see darkness along the edge here. We can see a sort of a jagged outline here. And we also see that the fact that this darkened part moves from this region to that region. So from the top left to the bottom left means that whatever object is associated with the sun losing light emission in that portion is moving extremely fast. It moves basically from here to there in about 15 minutes. The same thing happens with all the other wavelengths. And not only that, we can actually start to notice that different parts of the sun, slightly different parts of the sun, are visible in each of these. These boundaries are not exactly at the same place for each of the images, even though they are a few seconds apart. This is only 2 seconds apart. And yet we can, if we look at the line where this meets this curved line here, this one is larger than that one. We can see the same thing here. So it seems that a slightly larger portion of the sun is visible in the 171 angstrom image than in the 131. And we actually expect it to be the other way around if we were to look at the timestamp, since this one is from 2 seconds before. The same thing happens with all the other wavelengths. Again, we see the jagged line, we see the darker brown along this edge. Here indicating that the sun's losing light emission. Here again it's slightly jagged, but they did manage to put that cutoff line slightly further in. And here again the same thing, slightly jagged line. Here we see the curved outline curves outwards towards the darkness very clearly, and it's dark along the edge, showing that the intensity of the light in this region close to the boundary where the sun has gone dark has decreased substantially. So we have normal but reduced light emission due to the sun being weakened in this region. We have severely reduced intensity from this region, which is close to where the sun has actually stopped emitting light completely. There are no photons coming from there. And the fact that this curve, it curves outwards towards the darkness, not inwards. If it curved inwards, the boundary would look like this. And then we could say, well, it's due to an eclipse, an object is in front of the sun, because objects are curved and spherical, and so they would produce a boundary that will look like that. It will produce a boundary like that there, produce a boundary like that there. So we can see this is not an eclipse. The sun is losing light emission. It's emitting no photons from these regions below the lighted part at this time. And in all the wavelengths detected by SDO, including the visible light. As you can see, this is the visible light image. And the visible light images are also interesting because I've been noticing for many months that there is this outline behind the sun always. And this wasn't there in 2010. And this shows that there is another object behind the sun that is emitting visible light. I think that is the only explanation that I can give. There's an object there, I think. So, in conclusion, the sun is being affected by a huge number of stellar cores that are part of the Planet X system and that have become a part of our solar system. The sun has been weakened and destabilized, which is leading to stronger solar flares and CMEs, even as it is having trouble maintaining light emission and ignition at the top of the chromosphere. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.